Hello and welcome. My name is William Kresl and I'm going to talk about tunable performance matrix for acoustic liners. I will talk about the motivation, the low frequency acoustic liner concept, the low frequency performance matrix, ZKTL design process, the different matrix and process for each, and finally the conclusion. The need for small, lightweight liners comes from ultra-high bypass ratio turbofan engines, which cause significantly low frequency noise emissions. Conventional liners used today are impractical for frequencies below about 1000 Hz. Quantifying these liners with the LFPs are useful to compare different liner candidates to one another for quick iterations in the future. The goal is to discover if tunable performance metrics can be developed to discriminate between optimal liner designs for various noise profiles. Current lightweight, compact, low-frequency liner concepts, such as the folded core liner on the left, which is what we use in this study, and the membrane-embedded liner on the right, offer promising opportunities to develop practical solutions in the future. In order to compare different designs, the low-frequency performance metric, or LFP, is used to compare different designs based on relative acoustic parameters, which were used to create a non-dimensionalized performance metric. This LFP uses the variables such as beta, which is the lowest continuous frequency bandwidth where the absorption coefficient is greater than 0.6, m, which is the max peak value of the absorption coefficient that is within beta, and zeta, which is the frequency in which the line first crosses the absorption value of 0.6. The low-frequency performance metric was used in conjunction with the Zwicker and Cosen's theory of sound propagation in channels, also known as ZKTL, to predict the impedance of a liner. Optimum design configurations were then determined using the LFP. To do this, a cluster of possible configurations with different cavity lengths were chosen that were within the input target frequency range. These lengths are then optimized based on the LFP. Each resonator has a different depth and cluster. Once the cavity lengths are optimized, the phase sheet is then optimized for best performance. Using the ZKTL code, the LFP can be expanded to include additional parameters to generate tunable performance metrics for various design priorities. These metrics being the baseline, or LFP, the cubic lower bound, or CLB, the lower frequency max peak broadband, or LMB, and the average frequency normalization, or AFN. Each will be discussed in later slides. The variables used for these are similar to the LFP in the earlier slides, where B is the lowest continuous frequency where the absorption is above 0.6, M, which is the peak of the value of the absorption coefficient that is within B, G, which is the frequency at which the line first crosses the 0.6 absorption value, C, where the line comes back down and crosses the 0.6 value, U, which is the frequency of the max peak M, and finally the integral of the absorption spectrum above 0.6. These parameters are used as tunable quantities to affect the LFP. The use of the multipliers at the end of the equations are used to get non-integers instead of only decimals. The baseline LFP was initially used to select a set of candidate designs optimizing for a large bandwidth and a high absorption value. This LFP was compared against 12 different prospective liners, where the length of the cells are 2.5 inches long, 3 inches long, 4 inches long, and 6 inches long. Each different liner has a different number of cell groups. For example, the first liner has one cell group that is 2.5 inches long, two cell groups that are 3 inches long, one cell group that is 4 inches long, and 5 cell groups that are 6 inches long. For each liner was then calculated using ZKTL and the baseline LFP to get the LFP numbers you see on the right of the table. The best being the one that has 8 2.5-inch resonators, 4 3-inch resonators, 1 4-inch resonator, and 1 6-inch resonator. The graph for this liner is on the right and is color-coded with the best LFP for that result. The next matrix is the cubic lower bound, or CLB. This is similar to the baseline LFP, but the cubic lower bound matrix is used to optimize a peak at a low frequency. This is done by cubing the lower bound of the bandwidth. The best one being the resonator, that is one 2.5-inch resonator, two 3-inch resonator, one 4-inch resonator, and five 6-inch resonator. This is graphed against the baseline LFP to show the difference between them. The third matrix is the lower frequency max peak broadband LFP, or LMB. This LFP optimizes a large bandwidth that has a max peak at the lower end of its bandwidth. This is done by taking the U term, which is the frequency of the highest peak, and multiplying it in the denominator to optimize a low frequency value. The best liner from the list of 12 is the one that has three 2.5-inch resonators, seven 3-inch resonators, two 4-inch resonators, and one 6-inch resonator. This is again graphed against the best liners from the baseline LFP and the CLB. As you can see, the LMB has a broad bandwidth at a high peak at the lower end of its bandwidth. The final matrix being the average frequency normalization, or AFN. The AFN optimizes for best total absorption in a range. For this, an integral was taken using trapezoidal rule of the line that is above the absorption coefficient of 0.6. It was then divided by its range to make it non-dimensional. Of the 12 liners, the liner that has 7 2.5-inch resonators, 5 3-inch resonators, 1 4-inch resonator, and 1 6-inch resonator was the best. This is again graphed against the previous LFPs. Using these LFPs, 4 designs were manufactured and tested. Half-inch cells that are 1/4 of an inch in diameter were connected to get the desired length of the resonator. Design 1 and 2 were initial designs using the baseline LFP, along with previous knowledge and experience, whereas Design 3 was selected solely using the cubic lower bound LFP to get a narrow band low frequency, and Design 4 was selected using the average frequency normalization to get a wide broadband performance. These manufacturer designs were tested and matched very well to the simulated results. In conclusion, the tunable performance metrics such as the low frequency performance LFP, the cubic lower bound CLB, the lower frequency max peak broadband LMB, and the average frequency normalization AFN were investigated for selecting different noise profiles, especially for addressing low frequency tones and broadband low frequencies, and can be implemented using automated tools to help iterate through different designs to get an optimal one. These metrics in the future could also include structural parameters to optimize mass, volume, stiffness, or strength to provide a more holistic means of evaluation. References. Finally, I would like to thank Oklahoma Center for the Advancement of Science and Technology and Cowboy Technologies for their support. Thank you and have a nice day.